and today we will discuss about these fiber optic light sources and the different sources which we come across in day-to-day life are the sources like the light which is coming from the sun, the light which is coming from the stars, and we can also produce light from candles, the light from incandescent bulb, and the light from tube lights. Now, we will try to understand whether these sources which you have mentioned can be used for this fiber optics or not. If not, then why you cannot use these sources as fiber optic sources? And having said that, we will try to understand the basic mechanism, the principle by which these fiber optic light sources can operate. And then we will see what are the different light sources which are used in this fiber optics. Now, to begin with, we will try to understand what are the different requirements for these fiber optic sources. Now, as you know, this fiber optic source is basically used to produce the signal, and the signal is to be introduced into this fiber. As a result of which, the physical dimension of the source should match with the dimension of the fiber. And as you know, that the dimension of the fiber is of the order of micrometer. Therefore, the dimension of the source should be also of the same dimension or of the same order of dimension. So this is the first requirement for the fiber optic source. The second requirement, as you can see, is the narrow radiation pattern. And the narrow radiation pattern means the beam width which is produced by the source. So the beam width of the source for this fiber optics should be as small as possible. Otherwise, a large fraction of power will be lost when you will couple this source with this fiber. And the third property which this source should also satisfy is what is known as the linearity. When we talk about the linearity of the source, we mean that the relation between the output power and the input driving current for the particular source should be a straight line. Otherwise, this source cannot be modulated, and as a result of which you cannot use this source for any practical applications. Then the next condition which is required for the fiber optic source is the fast response time. That means as soon as you will apply this driving current, this source should emit the light. So the time gap between this application of this input current or the input voltage and the power should be as small as possible. And of course, the source should produce adequate power so that it can be introduced into this fiber and it can travel for a long distance in the optical fiber. Besides this narrow radiation pattern, another requirement for fiber optic source is the narrow spectral width. By narrow spectral width, we mean that the number of wavelengths which are contained in this source should be as small as possible, so that when the signal will travel along the length of this fiber, this signal should not disperse much, because as you know, that the dispersion of the signal basically is decided by this wavelength. So to avoid this dispersion, to avoid the spreading of the signal in this optical fiber, we should also see that the number of wavelength contained in the emission of the source should be as small as possible. And the other criteria like stability, efficiency, and reliability and cost should be always to be considered for any device, and hence we should also consider this criteria for choosing or selecting a source. Now, if you'll ask me, what are the different sources which exist that can satisfy all the requirements which you have mentioned? Now, as I have mentioned earlier, that there are different sources like source from sunlight, source from stars, source from burning of wood, source from this candle, and this source, the light from this incandescent bulb. So all are some examples of this source. But all the sources which we have mentioned right now are not this fiber optic source because they do not satisfy either one of these conditions which I have mentioned before. Therefore, I cannot use the sources for this fiber optics. Then what are the sources which can satisfy all the requirements which were mentioned? Then we can say that this is either the light emitting diode or this laser diode. So the light emitting diode and the laser diode are known as the fiber optic sources. So then what we will do is we will try to understand this basic principle of this light emitting diode and this laser diode. Now, the basic principle of this LED or LD, which is based on the semiconductor, and this LED or LD is basically a forward bias PN junction. So when I say a forward bias PN junction, then we mean that a P type of semiconductor and N type of semiconductor should be formed. In fact, they should be sandwiched to form a PN junction. And when you will apply a bias, in fact, a forward bias, then the electrons and holes will be injected into the small portion which is created near the junction, which is called as the depletion region. So when these electrons and holes are injected into the depletion region, then there is a possibility of recombination between these electrons and holes. And when this electron hole recombination takes place, there will be light which will be emitted from this junction. So this is the basic principle of the light emission in a semiconductor source like a PN junction. Now, LED and this laser diode both are based on this semiconductor PN junction, though their principle of emissions are different. For example, in LED, the light emission is due to a process called as spontaneous emission, whereas in case of LD, the light emission is due to a different process which is called as the stimulated emission, which we will discuss a little later. Now, just to review what we have studied in earlier undergraduate classes, because this is essential to understand the basic principle of LED or LD. So we will take some time to just review what you have studied in your semiconductor physics in your undergraduate classes. Now, the diagram which I have shown is what is called as an intrinsic semiconductor. And as you know, in a semiconductor, there is a valency band, there is a conduction band, and at absolute zero temperature, the valency band is completely filled, the conduction band is valency band is completely filled, and conduction band is completely empty. And if you will increase temperature, then the electrons from the valency band will be excited through this forbidden energy gap and will reach to the conduction band. As a result of which, there is a creation of electron hole pair. And this electron hole pair is responsible for the conduction of the semiconductor. So therefore, if you will take the intrinsic semiconductor, as you can see here, that the distribution of hole concentration and the distribution of electron concentration is something similar, right? So this is the situation in case of your intrinsic semiconductor. Now, as we know that the concentration of hole and the concentration of electron in case of intrinsic semiconductor is very, very small, and therefore we cannot get any practical application out of this intrinsic semiconductor. So to get some practical application to this intrinsic semiconductor, you have to dope this intrinsic semiconductor either by a pentavalent impurity or by a trivalent impurity. So when you will add a pentavalent impurity to an intrinsic semiconductor, then what type of semiconductor which is formed is known as N type of semiconductor or N type of material. This is because when you will add this pentavalent impurity to a intrinsic semiconductor like germanium or silicon, which valence is 4, and the valency of the impurity is 5. Therefore, when you are adding one impurity atom, then one electron will remain unbonded, and therefore, with a large number of impurity atom, you will see that a large number of electrons will be produced in this material. And this is in addition to the electrons and holes which are present in case of intrinsic semiconductor. So therefore, what will happen in this case is the number of electrons will increase compared to this number of holes. Therefore, the conductivity in these materials will be dominated by these electrons, the negative charge carriers, and therefore these are called as N-type of materials. And as you can see in this band diagram, this electron concentration distribution is now much more than this whole distribution in the valency band. So this is the case of a N-type of material. Now, similarly, if you add a trivalent impurity, instead of forming an electron, there will be an extra holes which will be formed, and therefore you will find a large number of holes in addition to this number of electrons and holes which are there in case of intrinsic semiconductor. So therefore, hole concentration distribution is much more in case of if you compare with the electron concentration in the conduction band. And therefore, the conductivity is dominated by these positive charge carriers, which are known as hole, and therefore this is called as P type of material. So therefore, in a P type of material, the conductivity is dominated by these holes, so the positive charge carrier, whereas in case of an N type of material, this conductivity is dominated by the negative charge carriers, which is called as the electrons. Now, if you see the Fermi level in case of N type of semiconductor, this is towards this conduction band, whereas in case of P type of semiconductor, this is towards this valency band. Now, suppose you will form a PN junction using a P type of N type of semiconductor, then what essentially will happen is these two Fermi levels which were there will try to adjust to form a single Fermi energy level. So therefore, as you can see here, when this PN junction is forward biased, then what will happen is this electrons from this N type of semiconductor will be injected into this depleted region. Similarly, the holes from this P type of region will be injected to the depletion region, and therefore the electrons holes will be found in the small region which is called as the depletion region. Now then, the electrons and holes will recombine, and with this recombination, you will get light. And this is the basic principle of emission of light in a semiconductor. But what is the problem which is associated with this simple p-n junction structure? Now, as I've said, this recombination is taking place in a small region, which is called as the depletion region, and the depletion region dimension is of the order of micrometer. And therefore, light is expected to be emitted from a small region whose dimension is micrometer, and which is, of course, the dimension of the fiber. So, if you can ensure that the light is emitted from a small region of the order of the dimension micrometer, then there is a effective, uh, you know, uh, uh, effective coupling of light from the source to the fiber. But actually, this doesn't happen. The reason being, when we say that the electrons and holes are injected into this depletion region, which is a very small region, we cannot give guarantee that there are no electrons outside this depletion region. So there may be some electrons or there may be some few electrons which are there outside this active region. So when these electrons are there outside the depletion region, they may also recombine to produce light. And if they will produce light outside this depletion region, then the light will be emitted from a broader region, not in a smaller region like of the dimension of a few micrometer. So therefore, if you are not ensuring the electron hole recombination in the small region, then you cannot say that the light will be emitted from a very small region. It may be from a broader region. So therefore, this is one of the difficulty in getting light from a small region, that is from the depletion region. But suppose we will assume that by some mechanism we have restricted these electrons and holes in the depletion region. Therefore, no electrons and hole will recombine outside the depletion region. That's fine. But when these electrons and hole will recombine, this will give you light. And light, as you know, is some bunch of photons. So now, can you give guarantee that the photons which are produced inside this active region will be constrained in this active region or the depletion region? You cannot give guarantee. So therefore, the photons, though are produced, the light, though is produced in a small region called as the depletion region, there is a finite possibility that these photons will come out the active region or the depletion region and will be emitted outside the depletion region. And if this happens, then there is again a problem that the light cannot be emitted from a small region. So these are the some of the issues which are there in a simple PN junction when you will use this structure for this emission of light or to produce light. So the first problem which I was talking about is something, the problem associated with the carrier, and we need a mechanism to confine these electrons and holes in this depletion region. And this is called as the carrier confinement. We want that the electrons and holes should only recombine within the small region, which is called as the depletion region. Similarly, the mechanism, or you can say the principle by which you can restrict these photons in this small region called at the depletion region is called as the optical confinement. So what I want to explain here is, if you can ensure this carrier confinement in optical confinement in this PN junction or this PN diode, then it is possible that this PN junction or diode will emit light in a small region whose dimension is of the order of micrometer. And a simple PN junction cannot be used to realize this carrier confinement and optical confinement. So therefore, you have to think some better alternative to realize this carrier confinement and the optical confinement. So I will stop my discussion here for the structure. I will come to this material aspect. Then again, we will go back to the structure where we will see how you can realize this carrier confinement and optical confinement by using a double heterostructure structure. Now, coming to this material aspect of this p-n junction, you might have studied in your undergraduate classes that uh, a source which will emit light, or this LED, the light emitting diode, is basically uh, fabricated from a direct band gap semiconductor. It is not from an indirect band gap semiconductor. So we will take some time to understand what is this direct band gap semiconductor and indirect band gap semiconductor, and what are these materials. And then we will see how these materials can be used for this PN junction. Now, the standard examples of these semiconducting materials, if you have studied in your earlier +2 or +3 classes, is silicon and germanium. But silicon and germanium are not the direct band gap semiconductor, they are indirect band gap semiconductors. But there are also some semiconductors like compound semiconductor, which are formed by combining two different elements like gallium arsenide, indium arsenide, aluminum arsenide, gallium phosphide, and all. They are called as the direct band gap semiconductor. Now, what is the basic difference between this direct band gap semiconductor and indirect band gap semiconductor? Now, if you will see this Venn diagram of the material like gallium arsenide, which happens to be a direct band gap semiconductor, the band gap is the uh, you know principle or the Venn diagram of that particular material will decide whether this is a direct band gap or indirect band gap semiconductor. For example, if you see this gallium arsenide, the top of this valency band and this bottom of this conduction band, they lie for the same value of this K. Whereas if you see this Venn diagram for silicon, the top of this valency band and the bottom of this conduction band, they lie for two different values of K. And therefore, this is a indirect band gap semiconductor. Now, what plus point you will get in direct band gap semiconductor? The electron hole pair creation is somewhat easier compared to indirect band gap semiconductor. This is because the electron can transit from the top of the valency band to this bottom of this conduction band. Whereas in case of indirect band gap semiconductor, this is not possible because if there is a transition from the top of this valency band to this bottom of the conduction band, there is a violation of law of conservation of momentum. So therefore, initially it has to go somewhere corresponding to the same value of K, and then it will come down to this, bottom of this conduction band. In other words, you can say that if you want to take this electron from the top of the valency band to this bottom of the conduction band, you need an extra particle called as phonon, and this is somewhat called as phonon mediated transition. So the transition will not take place so simple as in case of direct band gap semiconductor. It needs some extra particles called as phonon for this transition. Therefore, this transition is somewhat difficult. In other words, this electron hole pair creation is somewhat difficult in case of indirect band gap semiconductor than this direct band gap semiconductor. So, because this light emission is due to this electron hole recombination, therefore, what you want initially is the electron hole pair creation. And as electron hole pair creation is easier in case of direct band gap semiconductor, therefore, direct band gap semiconductor like gallium arsenide is preferred to indirect band gap semiconductor like germanium or silicon. So now we have explained what is this direct band gap semiconductor and indirect band gap semiconductor. And these are some of these examples of direct band gap semiconductors and indirect band gap semiconductors. Now with this, basic principle of the p-n junction and some idea about this direct band gap semiconductor and indirect band gap semiconductor, you will try to understand this double heterostructure configuration of this p-n junction, which is actually a battery structure to realize this carrier confinement and this optical confinement. Now, let me first explain what do we mean by this double heterostructure. Now, in the diagram, what you have mentioned is what is known as the double heterostructure configuration. Now, what is this double heterostructure configuration? As you can see, I have a N type of semiconductor at the middle, which is surrounded by two materials. To the left, there is N type of material, and to the right, there is P type of material. So in principle, the middle layer, the N-type layer, which is called as the recombination region where the electron holes will recombine, is surrounded by a semiconducting layer to the left and also another semiconductor layer to the right. And this is actually is the double heterostructure. Now, besides this double heterostructure, you can see also there is a layer which is called as the substrate to the uh, uh, top of this metal contact. If you see the metal contact, then above that there is a substrate. Now, substrate is basically the platform where you will grow these different layers. In fact, the middle layer has a name, that is the recombination layer or the region, and the semiconducting layers which will surround this recombination region or the layer is called as the confinement layer. So there is a confinement layer left to this recombination region, and there is also a confinement layer right to this recombination region. So therefore, the double heterostructure configuration is made out of three different layers: one recombination layer or the region, and two confinement regions of layers. Now then, to grow this double heterostructure, you need a substrate, and therefore you have to take a substrate on which you have to grow this double heterostructure. Now, if you see to the right of this confinement layer, uh, in fact, this confinement layer, there is another layer which is used, which is called as metal contact improvement layer. Now, why this metal contact improvement layer is used? And this layer is basically used because to improve this contact. To explain this more elaborately, let us try to understand what is the contact in the left-hand side. Now, I will come to this different materials later, but for the time being, let us assume that the material which is used in this substrate is gallium arsenide. And the metallic contact material is, let us say, silver. So therefore, the junction which is formed at the contact is between silver and gallium arsenide. Now, if you'll see, suppose I will not give any metal contact improvement layers in the right, and you will simply put a metal contact over this confinement layer. Now, what is this contact here? Let us say put again silver as a metal contact. Then the contact at the right will be gallium, aluminum arsenide, and silver. If you will not put a gallium arsenide metal contact improvement layer. Therefore, the metal contact which you are getting in the left-hand side is something different from the metal contact which you are getting at the right-hand side. And this will create a problem in the device efficiency. So therefore, what you will do here is you will put a same material layer as that of the left-hand side, and then the contact which you will get at the right-hand side is again gallium arsenide and the silver. And this is why you have to put another layer which is called as metal contact improvement layer. So therefore, the whole structure is formed like this. You have a double heterostructure. Then you have to take a substrate, and to the right, you have to take a metal contact improvement layer. And of course, two metallic contacts are to be given so that you have to give this to this, bias. That means you have to connect to the two terminals of the battery. So this is all about the structure. Now, once you have understood the structure, now let us try to understand the band diagram of this heterostructure, double heterostructure, and the variation of refractive index. Now, if you'll see this, the variation of band gap, then you can see that the band gap in this recombination region is smallest, and the band gap in the confinement region is something more. So intentionally, I have varied this band gap of these three different regions so that when these electrons and holes are injected, then you can see that due to the suitable, design of this, different band gap, there is a barrier which is formed at this recombination region to the electrons. And similarly, there is also a barrier which is formed at the recombination region due to holes. So when the electrons and holes are injected due to this quad biasing, what will happen is the electrons and holes cannot come out of this barrier, and therefore they will be confined within this recombination region. And therefore the first condition which we are talking about, that there should be a carrier confinement, is realized. And this is realized by suitably adjusting the value of band gap of recombination region and confinement region. Now, coming to the second criteria, that is the optical confinement. You can see here that we have adjusted the refractive index of different region, and intentionally we have made the refractive index of this active region or the recombination region more, and the refractive index of this confinement region something less. So that when this light is trying to go out of this recombination region where the refractive index is more, has a possibility of this total internal reflection, so that while it is trying to escape out of this recombination region, which is surrounded by a low refractive index region, it will bend again towards the same medium. But as you know, this is possible only when the second condition for total internal reflection is satisfied, because there are two, you know, uh, criteria which are to be satisfied for total interreflection. The first one is the refractive index, the light should travel from a denser medium to the rarer medium, which is satisfied in this case. But the second condition is also to be satisfied, that is, the angle of incidence should be greater than the critical angle of incidence. Now, how this condition is realized to confine the light within this recombination region? This is because the dimension of this recombination region very, very small, that is 0.3 micrometer. So because this dimension is very small, a light beam will strike to this interface with an angle nearly equal to 90 degree, and therefore the angle of incidence will be always greater than the critical angle of incidence to satisfy the total interreflection. So therefore, the light will be constrained to be inside this recombination region. So therefore, by using a double structure configuration, as I have mentioned here, by suitably changing the band gap in these three different regions, by suitably changing this refractive index in these three different regions, we are now in a state to realize the carrier confinement and optical confinement. And this carrier confinement and optical confinement will ensure that the light will be emitted from a very small region from this recombination region, which is sometimes also called as active region, whose dimension is of the order of few micrometer, and here this is 0.3 micrometer. So this is all about the double heterostructure configuration. We will stop here, and maybe in the next class we will continue with how this double heterostructure can be utilized to realize a light emitting diode and to realize this laser diode. Thank you very much.